Hey guys, so this video is about simplifying radicals, and this topic is pretty much the backbone of the rest of the chapter. So if you slack here, you're going to have troubles pretty much in all the sections coming up and then the entire test. And then there's one more chapter out there on quadratics where this comes up a bunch, and so kind of if you miss this section, it'll bite you like 7 or 8 times down the road. So this is definitely not the place to slack. So we're going to simplify these radicals, and it's kind of in two parts. There's the ones that are not fractions, just like this, and then we're going to see some fraction ones later. These ones are kind of tough. If these are where you hang up, it's not the worst thing. That's like kind of one question or 1 or 2 questions on a test. This is the part that you really need to get for kind of going forward. If you don't have a good grasp on this, that really messes you up for about half of the remaining material of the course. So we're starting off with these, and this is kind of the criteria we have to meet for a radical to be simplified. The first one's all perfect squares, cubes, etc. have been removed out from under the radical sign. So I'm not saying that very precisely, but basically what I'm trying to say is if I have a square root, if I have a perfect square hiding in there, I need to get it pulled out of there. So like if I have a square root 4, I need to make it a 2. Likewise, if I have a cube under a cube root, I need to simplify that out. We don't get to have fractions under the radical, so nothing like that. And then there's no radicals in the denominator of a fraction. So if I do have a fraction, what's downstairs can't be a radical. And so this is kind of the second half of the homework. The simpler ones of these are important. The really complicated ones of these, they don't come back that much. Maybe you run into them here and there, but this first part, this is the really important piece of this section. Okay, so here it goes. We have this property here that says if I have two things multiplying under a radical, I can think of them as two separate radicals, if that might be helpful. And so looking at 24 and trying to figure out how to simplify it, I could rewrite 24 multiplying 4 times 6. And then using this property, and you don't do all these steps every time, but this is just to kind of show why it works. If I think of that as root 4 times root 6, then this becomes, square root 4 becomes 2. I can simplify that, and root 6. So that's what we mean by simplified form of radicals, that if there's a perfect square under the radical, under a square root, we get that out, and likewise with third and fourth roots. So I'm going to do some more examples on this. This is a really great place to have that. Let me see if I have it over here. Nope, that's the exponent one. It's the sheet with all the squares and the cubes and the fourths and the fifths. This is where you're going to like that. Because you look at this 300, you're thinking, okay, so what's the biggest perfect square that divides in? If you have that sheet in front of you, I'm going to find it. Here we go. So this one. So you're looking at 300 and you're looking at the squares, and then like the 100 will hopefully kind of jump out at you as, oh, okay, that's the way to rewrite this. So if I do this as square root of 100 times 3, and you don't have to rewrite it in separate steps here. You can just think, okay, square root 100 would make a 10 out front, and then that 3 stays behind. A habit that I have is to always put whatever the perfect square is. So on this one it was the 4, on this one it was the 100. I write that first because it's what's going to come out, and it just kind of keeps me from like pulling the wrong number out, just sort of not paying attention to what I'm doing and writing it backwards. So I found that actually kind of helps me quite a bunch to not kind of write dumb stuff down, which I pretty much will probably jinx myself to do that now. So this one we got cube root of 108, and so if we're looking at our list of perfect cubes, we could try and see if 8 went in, and then that wouldn't work, and then we could try 27, and then we'd figure out that goes 4 times. So this is the cube root of 27 times 4, and so then cube root 27 would make a 3, and then cube root 4 is left behind. Remember, 4 is not a cube, it's a square, so it doesn't do any good under a cube root, it just stays there. 448, so this one is, if you tried your cubes, if you tried 8, that would work. But then you need to try, and it would be 56 would be left, so hopefully you would notice there's another 8 in that 56. So the biggest cube that goes in, you want to find the biggest one, would be 64 times 7. So the cube root of 64 is 4, and that will leave behind cube root 7. 1250, and we're looking at fourth root. So if we look at our fourths, we got 1681, 256, and then like 625 kind of jumps at me as, ending in a 25, this ends in a 50. That's looking pretty good. So I would try that one and find that it went twice. So this is going to be the fourth root of 625 times 2 is how I'm thinking of it. So the fourth root of 625 was 5, and then fourth root 2 is left behind. And then here, 352, fifth root. So those ones get really big really fast. And so if we just look, try the first one to go 32 and see if it goes in, it does. And it looks like it goes in 11 times. So this is the fifth root of 32 times 11. And the fifth root of 32 is 2, and then fifth root 11. Okay, I'll go through these next ones. These are the ones I would have you guys try in class. So 63, that would be 9 times 7, so square root 9 would bring out a 3, and then 7 stays behind. 80, so you might try like 8 and 10, but that doesn't really do you any good because neither 8 or 10 is a perfect square. And so you might notice 4 works, but that leaves 20, and there's another 4 in there. So that means the 16 is going to work. So if you do 16 times 5, and even if you did the 4 and still had a 20, then hopefully you notice the other 4 and you pull that out, you end up the same spot. But 16 times 5, so then that's going to be a 4, and square root 5. 175, so 25 goes into that one. So it'll be 25 times 7. And so square root 25 is 5, and then root 7 stays behind. Cube root 189, so that one is 27 times 7. So 27 times 7. So maybe first you try 8, and then that doesn't work, and then you try 27, and then you'll see it goes 7 times. So cube root 27 would bring out a 3, and then cube root 7 left behind. 243, so 243 is under a fourth root, and if you go up to 81, that's the one that ends up working. So that is fourth root of 81 and times 3. And fourth root of 81 is 3, and then fourth root 3 left behind. And fifth root of 96, another 32. So 32 times 3, so fifth root of 32 brings out a 2, and fifth root of 3 is left behind. Okay, so then for this next set, we get both numbers and letters. And remember we looked at the letters where we can use the idea of division. For a square root for every pair, 1 comes out. For a cube root for every 3, 1 comes out, so I can just go 3 goes into 10 how many times, and that's how many comes out, and then whatever's the remainder would stay inside. So I'll show that with these ones. But then we also have the numbers to contend with, and so first I like to try to figure out kind of what I'm doing with the numbers. And so for this 405, what I might do on that one is try dividing by 5, just because I can see 5 goes in and it's going to get me a smaller number. And then that would have given me that this is 81 times 5. And I don't necessarily rewrite the whole root, but I write myself that much so that as I'm kind of simplifying, I have that as sort of a visual cue, so I don't kind of forget what pieces I just did. So if I'm taking the root of all this, then I'm going to go square root of 81, and that's going to bring out a 9. And then what I do is I just leave myself some room for the x's and y's coming up. And I'll just start a root down here and then throw that 5 in so I don't kind of lose any of the pieces as I'm working through this. And then I'm kind of envisioning that little 2 right here that we don't really write but is handy. So 2 goes into 7 3 times. So x cubed comes out, and then there's 1x left over because 2 goes in 3 times with 1 left over. And then for the y's, 2 goes in to 10 5 times. So y to the 5th. And then none left over. So that would be your simplified form. For this next one, let's see, 128. So that's going to be a 64 times 2. And so cube root of 64 is a 4. And I'll leave some space. And throw the 2 back in there. And then I can go 3 goes into 10 3 times with 1 left over. And 3 goes into 14 4 times. So y to the 4th with 2 left over. So I just kind of work each number or letter until it's done. And then that keeps me pretty organized. And then this last one for me, at least in this part, 972, so this will be 243, which is our 3 to the 5th. And again, I would be getting that right off of that list that I had out. It's not that I know what 3 to the 5th is. I would look at, I'd figure out what 3 to the 5th is and then try dividing that in, or I'd look at the list. So the 5th root 243 is 3. And then 5 goes into 12 twice with 2 left over. Oops, I need to throw that 4 in there so I don't lose that. And 2 left over on x. See, as soon as I kind of deviate, you see what happens? I start missing pieces. And then 5 goes into the 29 5 times. So y to the 5th with 4 left over. Okay, these would be the ones that have you guys try. So 80, so that's probably a 16 times 5. 16 is 2 to the 4th. So we're going to, 4th root of 16 is going to bring out a 2. I'll leave myself some room. And then 5 stays inside. 4 goes into 7 once, so 1x comes out with 3 left over. And 4 goes into 16 4 times with none left over. 135 is going to be, what is 135? 27 times 5. So cube root of 27 is going to be a 3 out, and then there's going to be a 5 left inside, whoops, with my index, and then 3 goes into 7 twice with 1 left over. 147, so that is 49 times 3. And again, you would just try, divide by 4, no, divide by 9. You just kind of go up until you hit the one that works. Or you can try dividing this by 2, 3, 4, smaller numbers just to see if you can get something to break it up a little bit so you can kind of see what's in there. So anyhow, this will go 7 on the outside, and I'll leave some space, 3 on the inside. And again, I always just think of the little 2 there. So 2 goes into 12 6 times, and 2 goes into 10 5 times. And so I didn't need all that. So just the 3 left in. Number 7, so let's see, this is 243 times 2. And 243, 5th root of that is 3 again. And then I'll leave a little space. And 2 stays inside. 5 doesn't go into 2, so that would just stay. And then 5 goes into 11 twice with 1 left over. 88, so that's going to be an 8 times 11. So cube root of 8 brings out a 2, and then I'll leave some room. Cube root of 11 is still there. 3 goes into 9 3 times, none left over. 3 goes into 13, that would be 4 times with 1 left over. And here we got square root, so 9 times 5 would be 45. So 3 comes out, and 5 stays in. We'll think of our little 2. 2 goes into 17, 8 times with 1 left over, and 2 goes into 12 6 times with none left over. Okay, so now we're getting to that second part where we're going to do what's called rationalizing the denominators. And so for these simpler ones, that's a pretty useful skill, especially a trig. You'll do a lot of that. And you'll see this a bit in algebra. Some of them get kind of crazy hard, and you can figure they're once you figure out the trick to them, they're not bad at all. It's just kind of seeing the pattern. So hopefully I can help with that. So what we do is we can't have a radical in the denominator, and so the trick is just if it's a square root, if I just multiply it by another by itself, then I get square root 49, which is just a 7. So if I multiply a square root by itself, that undoes the root. But I can't just multiply by root 7. I have to multiply by root 7 over root 7 so that it's really a fancy 1. So then that's going to change the numerator also, which is fine. It's just that's what happens. And then we get 3 root 7 up top, and we just write those next to each other. The same as like if this was an x, think of it as like 3x. And then downstairs we're going to get root 7 times root 7. And so you could do that's square root 49. We could do this. And then we could go one more step and go, so then that's 3 root 7 over 7. And we have to do, that's the whole step. That's why we're doing this, is to get that 7 down there. I don't love stopping off here. I really want to encourage you that when you see root 7 times root 7, you think it's 7, and that's it. It doesn't matter what it is. Root A is A. And that's a really, really handy thing, because in these upcoming sections, we're going to do a lot of multiplying a root by itself. And if you don't have to kind of stumble around on what that is, it will be really glorious for you. So a root times itself, basically what's happening is, you're getting square root A squared, and then square root undoes square, and you just get A. Same way here, you get square root 49, and then square root 49 right back to 7. So yeah, it's a good one. I'd try to work that out. Number 9, so this little technique kind of halfway works, but I can't just like multiply it by another cube root 9, because if I did that, I'd have cube root 9 times cube root 9, which is cube root 81, and 81 is not a perfect cube, so that didn't really help me. What I need 3 of something. So I could go for 3 9s, but I could be slightly smarter than the 9 and realize that 9 is really, so that 9 right there, I'm going to think of it as a pair of 3s. And so what I really need, because I need to bring it up to a group of 3 so I can take the root, what I really need is one more 3. And so if I do cube root 3, so I'm just multiplying by 1, then that gets me up top 4 cube root 3, and then downstairs, after this example, I want you to just think, yeah, cube root 27 is going to go straight to a 3, but for this one, I just want to show that, yeah, see what we did? We made a 27, and then that's going to be cube root 27 makes the 3. So really what we're doing down here is we're taking the cube root of 3 3s, so what are we going to get? 3. So I don't really want to encourage you stopping off at this step, because people either they write plain 27 or they don't simplify, or they write cube root 3 or something. It's just you're making it a cube root 27, so it's going to make it 3. So the easier you can kind of glide from here to here, that's going to be better for you. It's just the same idea as this. So this one back to a square root, and so the only difference is now instead of just a 7 or something, it's a 2x, which is totally not a big deal. Also that it's a fraction under there, not a big deal. So we can just write it like this. And I could write it as that way too. Either way would work. But this seems a bit more natural just for how it's set up. And so I'm just multiplying it by itself because it's a square root, and I just need a pair of stuff. So I had a 2, I give another 2, I had an x, I give another x. So in the numerator, this stuff underneath, this is kind of like going backwards from the simplifying we did in the first half. So this will just be 5 times 2 will make a 10x. And then downstairs we're going root 2x times root 2x, and that makes 2x. So again, we're just trying to kind of glide past the fact that that's 4x squared for a second. You know, we could think about that, but that was, I just had to do some math, and I could get something wrong there, and I have to figure out, okay, that's 2, and then that's square root x squared would make x. There's too much thinking. It's root 2x makes 2x. That's it. Just try to get from here to there. Okay, here's where it gets a little crazy. So with this one, now we got kind of all sorts of things going on in terms of this denominator. So what we need is for all these bits to be groups of 3. Because if I have a cube root, I have to have 3 of something for it to come out of the radical. And that's what we're trying to do, is get the so that the denominator doesn't have a radical in it. So if I can make everything a perfect cube, then I can take the cube root, and then that's cool, I met that condition. So how can we figure out how to do that? So I got a 2, I got x, and I got some y's. So it seems like I kind of have 3 different things happening. And for each of these things, I'm going to need it to be in a group of 3. So what I do is I kind of set up, and this is just sort of my visual for how to think about this. So I set up something that kind of looks like a hangman. And so I have a 2 right now, I have an x, and I have a pair of y's. And so I set up 3 lines. My 2 looks like a z, sorry. I set up 3 lines because I need, the index on this thing is 3, so I need groups of 3. So if I have a 2, that means I need 2 more 2's, because I can only take the cube root of, what, 8? So this is our 8 right here. If I have an x, that means I need 2 more x's, because I got to be able to get this x out of the radical, so I got to give it two more friends so it can make its way out. And then I got a pair of y's, so I'm going to need 1 more y. So I'm going to come down here and write it a little bit bigger to make sure you can see all of it. So cube root 3, 2xy squared, and then I'm going to multiply that by everything I have up here in kind of the pink. So cube root, and we're still multiplying by a clever form of 1, it's just a really fancy one. So 2 times 2 would be 4. I got a pair of x's, so that's x squared and y. So 4x squared y. So then the numerator, that's going to be cube root 3 times 4. So remember, just kind of reverse. We had 2 radicals, so I can make them into 1. So that'll be 12x squared y. And then the denominator, and again, this is that step where I'm like, I don't think you should stop off at 8x cubed y cubed. I mean, you're just showing that, yeah, you just did all this work to make your perfect cubes. You know, but here's the thing, if up here, if I think of all of this under a cube root, which is really what's happening, because that's what all that is, cube root of 3 2's is 2. Cube root of 3 x's is x. Cube root of 3 y's is y. And that's what we're making it do by design. So I don't love the idea of writing out that step. I think it actually will confuse you more than it'll help you. I think if you realize what you're actually doing is making it do this, then it's a really easy transition. Okay, I'm just gonna move this one down here. I think it'll be easier for spacing. So okay, we got a 4th root of this stuff, and so I'm trying to clean up this denominator right here. So since I got 1, 2, kind of 3 things going on, and I need groups of 4, I'm going to sort of set up my little hangman with 1, 2, 3, 4, 2, 3, 4. So the index tells me how many lines, and I have 3 things, so I'll make kind of 3 setups. So with this 27, man, you do not want to think of that as a 27. You want to think of that as 3 times 3 times 3. So whatever's down here, break it down to its primes, and then you only put in 1 more 3 and not 3 more 27s, which would make it way difficult. We've got 3 x's, we'll toss those in, and a pair of y's. So then that helps me see I need 1 more 3, I need 1 more x, and I need 2 more y's. And so that's what I'm going to multiply up here by. So 3x and then y squared. 3xy squared. And So then that's going to make up top just 1 times this, 3xy squared. And then downstairs, right, it's just a big old 4th root of this stuff. So it's going to put out 1, 3, it's going to spit out an x, and it's going to spit out a y. And so this one, we'll do this one down here. So this is the 5th root of this stuff. So we'd have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And right now I have a 3, and I got a couple of y's. And so we'll do 4 more 3's and 3 more y's. So that'd be 9 times 9, 81. And 3 y's, so y cubed, 81, y cubed. Come over here with it. So 4 times 81, that would be 324. And then x, y cubed. And downstairs, once again, we're just taking the 5th root of, 5 3's. So that's 3, and then same idea on the y's. Okay, and these next few are the ones I would have you guys try. So I'll go through them a little bit quicker. So this, we got a square root, so we would just use the same as a 1. And so this time, notice the 8 isn't under a radical, so that's going to be 8 and then square root 5x. All you can do is just kind of write them next to each other like that. And then root 5x is 5x. And if something had reduced here with the 8 and the 5, I would need to do that, but in this case it doesn't, so we don't. For this one, let's see if I kind of think of it as this. I have a 4, but I want to think of that as a pair of 2's and a y. And then we'll go 1 more 2 and 2 more y's. So that would be cube root of 2y cubed. And then I'll just sneak down here with it. So that will be a 4 cube root 2y cubed. And then this would be, again, it's just this thing, right? So if we're going the cube root of 3 2's, it's a 2. Cube root of 3 y's is a y. And here's what I was talking about, is this 4 and this 2. And if you're like, can you cancel those? Yeah, because you got 4 times something and 2 times something. So it doesn't matter, as long as it's multiplying. If I have 4a and 2b, I can still, 4 over 2 is still just 2. So I can go 2 into 2 once, 2 into 4 twice. And so my reduced form is going to be 2 cube root 2 root. Sorry, I just figured out the silly thing I wrote up here. Let me fix that. That should be a squared. So I'm like, hey, that does not make sense. There we are. Okay, so 2 and then y squared. And then we canceled there, leaving that y. There we go. Let's see, for number 16, we'll think, so we got 3, 3, and 3. So 25 we'll think of as a pair of 5's, x squared, a pair of x's, and a y. And so that means we need 1 more 5, 1 more x, and 2 more y's. So putting those in, I'm going to get 5xy squared, 5xy squared. And so then up top, that's going to give me cube root, and these are both under, so I can actually multiply them. So 2 times 5 will be 10xy squared. And then downstairs, again, it's the cube root of this stuff. So I'm just going to get a 5, an x, and a y. You can take it out to 125x cubed y cubed if you want, but to me, it's better if you can just go from here to there. And then for this one, that one's a 4th root, so I'll just sort of make that down here. So 8, we don't want to think 8, we want to think 2 times 2 times 2, and an x, and then a couple of y's. So then, we need 1, 2, we need 3 x's, and we need 2 y's. So 2x cubed y squared, and 2x cubed y squared. So 3 times 2 under the radical, so that's going to give us a 6, and then x cubed and y squared. And then downstairs it's the 4th root of all these groups of 4, so it's just going to be a 2xy. And now here and here, these don't cancel because this is under radical, this isn't. And so those are not the same thing. If they're both under a radical, we could cancel. Or if they both weren't, we could cancel. But since they're in between, we can't. So these two are a little bit different. Kind of the deal on this is that this numerator is a bit more complicated than we're used to seeing. I could, eventually I'm going to multiply this by root 11z, top and bottom. But there's some things I could simplify first, and it'd be easier to simplify this if I hadn't multiplied it by 11 first. So I'm going to look at that 75 as a 25 times a 3 under there. Not a very good 2. We'll just go again. 25 times 3. And so that's what I'm sort of seeing under the radical, x6 y squared. And then 11z is sort of a separate thing. So I'm going to simplify this numerator first. And so I'm just going to say bringing out the 25 would be a 5, because square root of 25 makes 5. 2 goes into the 6, so that'd be 3 times. 2 goes into y squared once. And I just have that 3 left over. And then that's all over square root 11z. And now when I rationalize the denominator, when I do the bit with when I multiply the top and bottom by root 11z, so this isn't gonna, it'll be 33, there's nothing to simplify. But if I had done it back here at the 75, then I just make that 25 a little bit harder to get at by making it bigger. So for me, I prefer to simplify if I can first, and then rationalize the denominator. And then this will just be 33z over 11z. And nothing here that's the same top and bottom, so that would be where we'd have to leave that. Number 20 up here, so cube root of 64, that's a 4, so we bring that out. 3 goes into x, so into the 6 twice, so we get x squared out. And now I just have cube root y. And then I can deal with this 3z squared down here as kind of a separate step. So if I have 3z squared, 1, 2, 3, 3, so I have a 3 and a pair of z's. So that means I need 2 more 3's and 1 more z. So that would be 9z. And now 4x squared, and then let's go 9yz, so I'll just kind of go alphabetical. And then this is going to just be, cube root 3 cubed is 3, and likewise with the z. Okay, and these last couple I would have you guys try. So 24, that would be a 4 times a 6 in there. So taking out the 4, that would come out as a 2. And then I'll leave some room for x's and y's. And then put the 6 in. And that little invisible 2 goes into 6 3 times. So 3 x's come out. 2 goes into 9 4 times with 1 left over. And then that's all over root 5z. So from there I can go root 5z, root 5z. So that's going to be all of that, and then 6 times 5 makes 30, and then yz. And that's root 5z, so that's just 5z. And then this last one, so we can go cube root of 27 would make a 3 out. So cube root of 27 makes 3. 3 goes in the 4 once, and then with 1 left over on the x, and then the y would still be in there. And then downstairs we'd have cube root of 4z squared. So again, we don't want to think of 4 as 4, we want to think of 4 as a pair of 2's. So we're doing a little hangman thing. We'd have a couple of 2's and a couple of z's, and so we'll go 2 and a z. So up top we'll do a 2z, and same thing downstairs. So 3x, and then just go in alphabetical order here. I get 2xyz, and then cube root of 3 2's is 2, and then z. So that wraps up simplifying radicals.